pretty basic intro into Kaplan-Meier plots. Thanks for having me. So the title of this talk is, the truth is hiding in plain sight. So you can learn a lot from these plots. All right, so here's the example, the first example. I think we've seen so many of these. And what do you see here? You see the cumulative survival. So it starts out with what percent of people are alive. It shows it over time. It's sometimes called the Kaplan-Meier estimate. There are these numbers at risk right below the line that tells you at each time point how many people are still at risk. They could have the event in the next time period. And there are these little tick marks that go all along it. Those tell you that a patient is being censored. We're going to talk about what that means. And you can see that the red curve does better than the black curve. So pretty straightforward. We look at these like a million times. And there's like a lot of information hidden in these plots. So every time the curve dips, what happens? That means the event has occurred. So what happened between here and here in the high expression group? Something happened. What happened? How many individuals had the event from here to here? What's your guess? 10%? Yeah, it looks like a big chunk of the people, right? But how many individuals experienced an event, do you think, to cause the Kaplan-Meier to dip that big? Yeah, the red. My guess is one person. Okay, so one person had the event in this time period, and why does the Kaplan-Meier plot fall so much? As you can see, there's only 4 people at risk. I actually think there were 5 people at risk right when this event happened. And so 1/5 is 20%. And I think this drop is 20% of the distance from this red line to the baseline. So what the Kaplan-Meier plot is doing is for all of the people you've followed for a certain amount of time, it's taking the information you know, which is that 1 out of 5 people experience an event in this time, and extrapolating that to all people as if it would have occurred to everybody. So every time the curve dips, that means an event occurred. The number at the bottom shows you the number of people still at risk. And there are larger steps at the end of the curve because fewer people are at risk. So in the beginning of the curve, whenever something bad happens to one person, you can barely see it because it's 1 out of 273. But by the end of it, one bad thing happens to one person, you can see it real clear because it's 1 out of 5. And then 4 people are subsequently at risk, I think, at 100 months. All right, so that's generally what we see. So actually, this part of the curve has a lot more information than this part of the curve. There's an old rule of thumb that says when less than 10% of people are at risk, you should cover it up with your hand. You shouldn't even look at that. It's a very noisy estimate. Because you can imagine if something bad happened to Tom, Sue, and Mary, the curve could even touch, All you need is two more events and the curves are going to cross. All right. The vertical ticks mean that a patient is censored, meaning that we don't know what happened to that person beyond that time point. And you see a lot of vertical ticks on this plot. And the estimate of survival beyond any ticks is basically averaging the people that we know what happened to. So we call this a maximum information harvesting. Basically, we take information about anyone who enrolls in the study, as much information as possible, and we use all that information in making this estimate. And then when we don't know what happened to that person, we rely on what we know from the other people. So we're literally using every bit of information we can from this group of people. And there's a key assumption here, which is uninformative censoring, meaning that the people who we lost track of, who enrolled recently, who we don't know what happened beyond some time point, that the people that we do know that information for, that they're just the same kinds of people. They're no healthier, wealthier, or wise. They're indistinguishable. They're the same type of people otherwise. It's uninformative that those people dropped out because we can average what happened about the people we know, and we can get a reliable estimate as to what would have happened had we followed everyone out into the future. Those are the basics of the Kaplan-Meier plot. Now, sometimes you look at a plot and it's about overall survival, which is the time to event endpoint, the time until you die. And you can see the shape of the curve is rather smooth, but towards the end they're the bigger steps because there are fewer people at risk. But sometimes you look at a plot, it's something called progression-free survival. These cancer doctors are looking at. It's the time until you have tumor progression or you die, whichever comes first. And here, look at the shape of it. It's not a smooth curve. It looks like stair steps, right? It looks like something happens, and then there's a step, and there's another step, another step. So my question to you is, why does it have this appearance, the progression-free survival plot, rather than the overall? This one is smooth, and this one, it looks like something's happening at week 6. Then something happens at week 12. Then something happens in week 18. Why every 6 weeks something's happening? Any guesses? Correct. They get the scan every 6 weeks. The protocol says every 6 weeks we're going to look to see if the cancer's bigger. Does that mean the cancer grew on that day? No, it probably progressed sometime before. So this endpoint is binned. It's arbitrarily put into bins because that's the frequency with which we do the scans. And the shape of the curve will be very different if those scans were every 6 weeks or 8 weeks or 10 weeks. The longer the scans are apart, it will be more dramatic steps, but they'd be further apart. And actually, you can change the estimate of benefit by just changing the scans. You can change some of the hazard ratio, which we'll talk about. All right. This is an interesting Kaplan-Meier plot. It's in the reverse direction. Okay, it starts out with nobody has the condition and measures people over time. And what it's showing you is what happens when you get the Pfizer-BioNTech vaccine. This is the original vaccine randomized controlled trial. These people get Pfizer shot. It's 2 doses. Does anyone remember how many days apart the doses are? 21 days. And these group of people get placebo 21 days apart. This is time from first dose. This is the endpoint is the cumulative incidence of symptomatic SARS-CoV-2, which means you have symptoms, you feel unwell, and then you tell them you feel unwell, and then they test you, and you had to have SARS-CoV-2 to score on this plot. When does the vaccine start working? 10 days, yeah. 7 days maybe, 10 days, 11 days. So what does that tell you? It doesn't work immediately. Well, that kind of makes sense, right? If you just get the shot, you have to have some antibody production, blah, blah, blah. It takes a few days. And then the second thing that's got to happen is you got to get COVID, and COVID has some incubation period. Like you get COVID, you don't feel sick right away. Still takes a few more days. And all that's baked in, and the curves still start to split at 10 days. It takes some time for the vaccine to kick in, make antibodies, some time for you to get COVID and feel symptomatic, but by 10 days we can start to detect the difference. Okay? This is the randomized study. By day 21, the second dose, whatever it's doing, it's already pretty floored by then. I mean, the differences are so pronounced even from the first dose. This is why some of us are also skeptical of the need for like infinite number of doses for somebody, because you get a huge amount of the benefit from the first dose, particularly for severe disease. Okay, so curve split really early in this randomized controlled trial. This is an observational study. It's not randomized, okay? It's comparing people who happen to get a booster versus people who got 3 doses versus 4 doses. This is from the Israelis. Sorry, everyone got 1 booster, but it's 3 versus 4 doses, okay? The randomized study, any vaccine versus no vaccine, 7 days before those curves split for symptomatic COVID-19. In the observational study, this is survival. This is the rate of death, okay? I think it's death from COVID-19. What day do the curves split? Yeah, maybe. Is that possible? Is that plausible? Let's see another example. Anil Makam, who's a hospitalist here, he says there's something very fishy about this study because the control group and the 4-dose group, there should be some amount of time for the antibodies to be made, some amount of time for incubation, and then you don't die immediately when you get COVID. You still have some prolonged hospitalization. The curves are splitting far before the booster could possibly be helping you. So why, in this observational study, do the curves split faster than the booster can work? Yes, and what's the confounder? Correct. Who's the kind of person that runs out and gets the extra booster right away? It's not the same as the type of person who doesn't get the booster right away. And all those characteristics, how much they do all the precautionary things and how much they go out. Also, their underlying health. What if I were to tell you that you can see dramatic effects in rates of car accidents? The people who get the second booster are less likely to have a car accident. That just tells you they're different people. What if I tell you their all-cause mortality, their non-COVID mortality is dramatically different and also splits very quickly? So what you're talking about is this is not randomized. This group is different, and those differences are translating to this outcome. So how much of this is the booster's effect, and how much of this is the fact that these people are healthier, or more precautious, or otherwise different? The answer is it's impossible to tell. So this is Eric Topol. He has a very interesting figure. He says, COVID vaccines reduce the likelihood, severity, and duration of long COVID. And here's the Kaplan-Meier plot. When you get vaccinated versus not, that's the long COVID. How fast does it work to prevent long COVID? immediately. Is that plausible? Not at all. So we wrote this paper called Detecting Selection Bias in Observational Studies When Interventions Work Too Fast. It's not plausible in an initial randomized controlled trial. It takes 7 days before I even see a difference in symptomatic SARS-CoV-2. Now you're telling me you get long COVID benefits from the beginning. Now you're telling me you get a death from COVID-19 difference on day 10 from boosting. It's not possible. It couldn't work so fast. There's got to be some difference between those two groups in observational data. And that's why we randomize, because people who participate in medical interventions are often different than those who don't. Here's one that I thought was great. Real-world effectiveness of Paxlovid. 85% reduction in deaths, 55% reduction in hospitalization, independent of vaccination status, age. How quickly does Paxlovid improve survival? Instantaneous. Instantaneous. I didn't even fill the prescription. I was just thinking about it. Okay, so this suffers from many, many problems, which is, one includes guarantee time. Guarantee time means that if you get Paxlovid, there's a certain amount of time that was guaranteed to you, which was the time until you could get it and take it. In the control arm, you can die immediately. But in this group, you'd have to wait until you take the first Paxlovid pill, you know? I think this uses prescriptions as the start point. But either way, it's just too good to be true. I mean, even if you think Paxlovid helps, there's no way you can immediately reverse this. It's not like, you know, holy water. It's not immediate, you know, it can't possibly work. Okay, when we run a randomized controlled trial, and I showed you that first randomized trial is like 170 people and like 80 people in the other arm, I think many people think that like, oh, you know, well, you start your study and you got 100 people and you randomize them. That's not how the study works, you know. We don't have everybody on day one. It takes some time. Typically, the way we run randomized studies is we open our study in 2015. And in the first month, we put on 15 people. And next month, 17, then 20. Then finally, we get up to, we got a good clip going. We get 30 people a month, 30 people a month, 30 people a month, 30 people a month. And each month, we're randomizing about 15, 15, 15, 15, 15, 15. And finally, we get to the part of the study where we got enough people we have enough people to have met our pre-specified sample size plan. And then the next period is the observation period. So this is typically how we run randomized controlled trials. And then at some point, somebody comes along and says, hey, let's take a look at the data. This is the first time we're going to look at the data. And it's right here in, you know, middle of 2017. So the person who enrolled in the first month, how much time did they contribute on the study? 1 year, 2 years, and a few months. The person who enrolled right here, they may have only contributed a few months, 2, 3 months to the study. So if I want to make a Kaplan-Meier plot of what happened to this person in 1 year later, I don't know. It's the future, right? I'm looking right now. And so that's one of the reasons we censor somebody is because they enrolled recently on the study, and I don't know what happens to you in the future. But isn't it fair to assume that if you enrolled here, you could have easily enrolled here. You're not fundamentally different. And if I take the outcomes of people who enrolled in 2016 and extrapolate that to you, that might be a realistic estimate for what might happen to you. So that's the whole principle of the plot. So what are the reasons somebody is censored? There's a few reasons, okay? One, they enrolled recently. For overall survival, that's true. For progression-free survival, they enrolled recently. Number two, they lost to follow-up, okay? We don't know what happened to them. Actually, for overall survival, loss to follow-up is extremely rare in modern studies. Because even if you enrolled on my study, I know what happened to you. I can follow your social security number. I know whether you lived or died, you know? The other thing that could happen is, in the plot, there's only two reasons why the number at risk goes down. One is you had the event, you died. And then the other reason is you're censored. Okay, and these are the reasons for censoring. For progression-free survival, it's the same too. But is there a third one? What's a third reason you could be censored on an endpoint that's the time until progression or death that doesn't apply to overall survival? You didn't get the scan. What do you need for PFS you don't need for OS? The scan. You stopped coming to the scan. If you stop coming to the scan and you die at your house, I can still figure that information out. But if you stop coming to the scan, I can no longer use your information to figure out when you progress, because I'm supposed to do it every 6 weeks. You don't meet my protocol. You know, even if I scanned you later, I don't know if you progressed months ago or you progressed then. So I have to censor you. Okay. Now, what is progression-free survival? It's one of these composite time to event endpoints. It's the time until one of several things happen. In cardiology, we use the major adverse cardiovascular events, which is like the time until MI, stroke, hospitalization for heart failure, or death, whichever comes first. Actually, it's actually not perfectly standardized. It varies study to study. In progression-free survival, it's the time until one of four things happen. Okay, one, we measure your tumor at baseline. It's got a certain diameter, cross-sectional area, and volume. And it's a time until the person dies. That's the survival part. You enroll in this study, you die 2 weeks later, you have the event. There's new lesions on the scan. We scanned your lungs, there was nothing out of the ordinary. Suddenly there are new spots. The tumor gets bigger, but it's got to get 120% bigger, then we call it progression. Or if it gets smaller, if it shrinks more than 30%, we call it a response. And then here progression is measured from the smallest it ever gets, the nadir value. So progression-free survival is the time until one of the four things happen, three of which depend on you getting the scan. All right? So the patient has to get the scan. So I was reading this study a few years ago. This is everolimus and postmenopausal hormone receptor positive breast cancer. You don't need to even know what this is. This is a new pill. Pill's like $12,000 a month. It makes you feel really crappy. They're combining it with a hormone therapy versus placebo hormone therapy, randomized control trial. This was getting all the publicity. The FDA approves it. Everyone's happy. It's some wonder drug. And these are the results. This is why. The progression-free survival from everolimus exemestane is much better than placebo exemestane. There's a big difference here. Hazard ratio 0.43. P-value, so many zeros in it. Can't even put them all. Very significant. Okay, looks promising. That's true on local assessment, central assessment. This is really a real finding. So imagine my surprise. Oh, and then here it is, blown up real close. Big difference, okay? There's an old saying in oncology, if you can fit the laser pointer between the curves, you can give the plenary session. Here you can fit at least 10 laser pointers. This is a dramatic result in our line of work. But the overall survival was published a year later in the Annals of Oncology, and that p-value is 0.1426. Not significant. Actually, these curves are pretty much the same. And with extended follow-up, there is no overall survival benefit. So this drug actually prevents progression-free survival events, but it doesn't improve overall survival. It's kind of weird. And it costs $12,000 a month. It's got side effects. It's kind of weird. So why does this happen? How can a drug slow the time until the tumor gets bigger, but it doesn't make you live longer? Well, here's what the company says. The company says, look, this is all the other therapies we're giving that are watering it down. You know, we give the new drug, and look, you do so much better than the old drug. It's like so much better. But then you give all those other pesky old drugs, and at the end of the day, the overall survival is the same. And that's what happened here. They call it confounding by subsequent therapy. But I always ask myself, you know, if I was running a marathon race and somebody was selling me a $12,000 Gatorade at the start line, and they were like, oh, you're going to run the first 7 miles faster, but you can finish the race at the same time, I might ask myself, what's the point of that $12,000 Gatorade? You know? So I don't even think this is a good explanation. But there's one other thing that might be happening in this study that the company doesn't want you to think about, that we start to think about, and that is censoring. I was looking at this plot, and it has got the number at risk and the number of people and the outcomes and all these tick marks. I can't see all those tick marks, you know? I have bad vision. I can barely see all that censoring. So I took this number, 398 people are still at risk at 6 weeks on everolimus, and I drew a line up there. And I asked myself, we start out with 485 people, right? And in the first 6 weeks, it looks like, would you say that's 12% drop? It's 88% now. Can we say that? 88% here? So it looks like 485 people start, 12% have the progression event, and then the number here is 485 minus people who had the event, minus the people censored. So I can calculate. 485 times 12% is 60 people. So I expected to see 426 people here, but what I saw was 398. And that's a difference of 28 people, or 7% of people were censored at the first time interval on the everolimus arm. Okay, well, there are lots of reasons for that, okay? They could have just enrolled late, right? They enrolled in the last 4 weeks, and I'm looking at 6 weeks outcomes, right? That's a possibility. So let me do it for the control arm. There's 239 that start, 177 are at risk. I draw the line here, humor me, let's say it's a drop of whatever, 20-some%. I did do this in a very ultra-precise way with a really big screen, you know, very big screen, okay? And I calculate 239, 25%, 60 people had the event. Should be 179 people still at risk, and the answer is 177. It's almost the exact same. So here, less than 1% of people are censored in the first time interval. Now, 7% versus 1% censored at the first time interval. Is it possible the difference in censoring is due to late enrollment, like enrolling just in the last few weeks. Why or why not? Correct. No. Correct. It's a randomized study. They use block randomization, which means every so many 6 units or 12 units, they guarantee equal outcomes in the two groups. So how could it be 7% of people randomized and censored in one arm? You'd have to assume that it's being randomized 20-to-1 randomization. It's 2-to-1 randomization, but this is the percentage of the whole thing. It's not possible, late enrollment. They're being randomized more or less equally over time. There's something else going on here. So what is it about this pill that makes 6% more people not show up to the first scan than in the control arm where they get sugar pill? Why? Yes? Correct. They got to get the scan. And why aren't they getting the scan? Because they're getting really sick from the adverse events. That's what I think. They're not getting the scan for that reason. Now, why so much censoring? Because of toxicity. Now my follow-up question to you is the assumption of uninformative censoring met? The 6% excess people who don't show up, are they the same as everybody else? If I have 100 people on a randomized study, and some are 40-year-old women who are still running in marathons, and some are 72-year-old women who have high blood pressure and diabetes and chronic kidney disease, and they have mobility issues around the house, and they all start taking this pill with some toxicity, who's the one that's going to be the first to say, I can't go get that scan? Is it going to be the 45-year-old or the 72-year-old who's frail? The frail person, right? So what we're doing is we're removing people from one arm that are frail, I think. That's what I think is going on. And that's not uninformative. The people being censored are not no healthier, wealthier, or wise than those in whom we have follow-up. They're probably older, frailer, more vulnerable, more likely to have disease progression, right? That's what I think is going on. I think it's informative censoring. There's an imbalance in censoring. That's what we've proven, the 7 versus 1%. And I think it's informative that the people being censored are different than those who are showing up. So here's what I told Usama Bilal, who was a statistician guy at Hopkins, very smart, now he's a professor. I said, Usama, do me a favor. Take those curves from the study and digitalize it with your computer magic. And he did that. That's the dark bars here. And then I said, count how many people are censored at every time interval. And then he did that. He got all that. And then I said, every censored person, the Kaplan-Meier plot assumes that the outcomes among the people we followed are the same as they would have been in the people who were censored. But what if you assume that the censored patients do really good, they live forever? And what if you assume that the censored patients do really bad, they die immediately? And he creates these 3 curves. So red is what they actually observed. This is the favorable assumption. This is the unfavorable assumption for everolimus. Blue is what they actually observed. The dotted line is favorable assumption for control, unfavorable assumption for control. And the point here is just the curves can cross. That merely by changing the assumption, if you assume that the censored people here are slightly lower, you're quickly going to get no statistical difference between the 2 curves. Okay? It hinges on the fact that uninformative censoring is true of this trial. And I don't think it's true. I think that the people who stopped coming, that excess, was much more likely to stop coming because they didn't feel good. And I don't think that's an average person in the study. I think that's a vulnerable, frail person in the study. And I think there probably might not be any PFS difference here if you really equally measured it in both arms over time. And so when I look at the difference between the PFS and the OS, I have a different story. My story isn't this is a drug that all the subsequent therapies made up for. My story is this is a drug that doesn't make you live longer. It costs $12,000 a month. It has lots of side effects. And even the PFS benefit that you're all popping champagne over might be spurious because you have not had equal censoring. You have unequal censoring. And that's probably very fishy about this study. All right. So that's the first lesson, is that actually all this is in plain sight, the censoring. Okay. Now the story gets a little more fun. Okay, so this was Tito Fojo. He was my program director when I was a fellow at the National Cancer Institute. He was the biggest believer in looking for censoring. His office was riddled with papers and rulers, and he was drawing those lines everywhere, drawing. I said, Tito, I thought he was like trying to solve a serial killer with all the lines drawn on the wall. But then I realized he was just looking at censoring. Okay, so he realized that why do I have to draw these lines when they know good and well how many people are censored? The company knows that information. I shouldn't have to draw the line and make an estimate and count like I showed for you all. They should just report it, you know? So Tito went to David Collingridge, who's the editor-in-chief of Lancet Oncology, and Tito said, David, do me a favor. When you publish your Kaplan-Meier curves, put down below the plot how many people are censored at each time interval. And David Congren said, okay, sure, we'll do it. We'll make it a new policy. And they did it. And they started to put all this information, this number of people at risk, how many people censored, 0, 4, 7, 8, 10. And here it actually looks kind of balanced between the two arms. There's no big differences here, right? But he's telling you the information. Now it's right here. You don't got to get a ruler out. So David Congren is adding the information. Okay, this was going on for 3 years. And then one day, Kate Rosen walked to my office. She's a medical student. She said, I'm looking for a project. And I said, I'll think of something. I said, I know. About 3 years ago, the Lancet family of journals started to report the percent of people censored. Why don't we go back and collect every single study in the last 3 years and extract all of that data and look to see if there's any differences in censoring in that first time interval between the group that got the treatment and the group that didn't get the treatment. And let's plot all those studies in one figure and we'll make a paper out of that. And lo and behold, she did make a paper out of that. It's called Censored Patients and Kaplan-Meier Plots of Cancer Drugs, an Empirical Analysis of Data Sharing. Because this is what you did with data sharing. And here's what she found. Very clever figure, I think. She made it, not me. And here's what it shows. This is the sample size of the study. I think that Bolero study is like 500, or like, I don't know, 300, 400, 500, something like this. But we got studies that go up to 2,000 people sample size. And this is the early time interval, one of the first time intervals. And these dots tell you that more people were censored on the intervention. More people taking the new pill were censored. And I think if it sticks out like this, this is very similar to Bolero. I don't think Bolero is in this because Bolero was not published in the Lancet in the years of this. This is from Lancet. But this tells you that there's probably people being knocked off out of toxicity. There's something going on over here. On the control arm, way more people don't show up to the first scan on the control arm. That's weird. And the weighted average is ever so slightly not in the middle. It's ever so slightly that people on the control arm drop out more in the first time interval than people on the treatment arm. Does anyone know why? People on the control arm, they drop out ever so slightly more than people on the treatment arm. Why is that in these cancer trials? That's right, patient disappointment. Sometimes it's open label, it's not even blinded. And sometimes it's blinded, but they get a feeling, this doesn't feel like everolimus, it feels like some sugar pill. And I don't want this sugar pill, I want the drug. And so you can take your study and you can go to hell. And this weighted average, I think, does reflect, I think it reflects patient disappointment and people quitting. The person who quits the study, is that person as healthy, wealthy, and wise as the person who sticks with it? Who's the kind of person that starts a study and says, I got a bad feeling you're giving me something that I don't want, it's not good enough for me. I'm going to quit and see what else I can get out there. Who's that person? Is it the average person? Who's that person? I think it's...
I might do that.
Yeah, it's somebody with healthcare knowledge who's typically wealthy, well-connected. I might do that too because I know everybody in this business. I can call up whoever I want, get whatever trial I want. Yeah, I might do that. Call up somebody and they owe me a favor from something. I promise I won't review their next paper, something like that. Okay, so, all right. So I think that's also informative censoring going on there too, a different type of information. All right, a few years ago, I was reading this paper. It's called Lutetium-177 PSMA 160. I couldn't even pronounce it. It was like so complicated. All I know is some radioactive drug. The drug goes in and it binds prostate cancer and it delivers radiotherapy to it. And I know that the trialist was saying that you can't do a blinded study because you can take your iPhone and put it to your body and your iPhone camera will light up because it's a Geiger counter because it can tell that you got radiation in your body. So like, well, we can't do a blinded study because people can bring a Geiger counter and tell that they got this good stuff in them. And so we got to go up against a non-blinded study against control. And lo and behold, to get in the study, you got to get this PSMA positive lesion and no PSMA negative lesion, blah, blah, blah. That's not important. And then they take 832 people, and then they randomize them to lutetium PSMA, or what they call standard of care. Obviously, the standard of care is the standard of care here. And then they got this big PFS benefit. The like fancy radioisotope is just so awesome. And they live longer too. Like, you know, Prasad can't criticize us. We have an overall survival benefit. Like, this looks so good. What was the problem I noticed? I was reading this study and I saw there's some problem in there. The standard therapy could not include cytotoxic chemotherapy, radioisotopes, immunotherapy, or drugs that were investigation when the trial was designed, olaparib. And I thought to myself, but some of these are things that I would like to do in my practice. And then they say the permitted treatments included but were not restricted to the approved hormonal treatments like, oh shit, like Abby or Enza. No, 1 second. The approved treatments included, but were not restricted to ABI or ENZA, bisphosphonates, radiotherapy, denosumab, or glucocorticoids. Glucocorticoids, what is this, 1940? We treat prostate cancer with cabazitaxel. We don't use prednisone anymore. And ABI and ENZA, those are good if you've never gotten ABI or ENZA. But if you've gotten either ABI or ENZA, getting more ABI or ENZA ain't that good. And then I looked in the thing, and it said if you got standard care, what was your prior treatment? And 98% of people got ABI or ENZA, and then 86% of people got both ABI and ENZA, and 12% of people got more than 2 regimens at baseline. And what they hadn't gotten is cabazitaxel. Only 40% got cabazitaxel. The reason that caught my eye was we got a randomized study of ABI, ENZA versus cabazitaxel, and that's already got a benefit. So you should have randomized lutetium PSMA or cabazitaxel, in my opinion, because that's already beaten what your control arm is that you've called standard. So I'm already getting a little suspicious. This control arm's not so good. In fact, I think it's very bad. Well, this is a common problem. This is Derek Tao, who's a medical student at OHSU, who worked with me. We wrote a paper in The Lancet called The Choice of Control Group in Randomized Trials. Are we testing trivialities? Like we're testing our new drug against something that we don't do or we know is not going to work so well. And we did a paper on this, an original article by Talal Halal, who was now he's a faculty member, but at the time I think he was a fellow in Arizona. Analysis of control arm quality in randomized controlled trials. And what he found was in the genitourinary randomized trials, it looked like 1/3 of them use an inappropriate control arm that's beneath the best available standard of care. And that's what they're doing in this lutetium study. They're using a control arm that does not include cabazitaxel, which I think should be standard of care, and includes giving drugs that we already have given and that don't work when you give them over again. So I wasn't the only person who thought that this control arm was really crappy. Apparently the patients did too. The paper says, quote, after the trial started, there was a high incidence of withdrawal from the trial in the control group at certain sites and attributed principally to patient disappointment. After discussion with the regulatory authorities, we implemented enhanced trial site education measures. That sounds like something you do in Guantanamo, as of March 5th, 2019. Enhanced trial site education to teach them not to drop out because there's too much dropping out in the control arm. How much dropping out was there? And the answer is enhanced trial site education. Okay, the answer was a lot, 56%. And then it went down to 16%. But let me show that to you visually. I remember I showed you this figure from our paper. Where would this trial fit on this figure if I showed you how much dropout there were? And here's where it fits. It's off the charts. 56% dropout. They brought it down with enhanced trial site education to 16%. It has so much dropout from the control arm. Why do people on the control arm, when they find out they're getting ABI or ENZA, when they've already gotten ABI or ENZA or ABI and ENZA, why are they dropping out? Because they know that's terrible. They know that's like basically malpractice. They know that cabazitaxel is out there. They know that they can get other things. Who are the people who still stay? Is that the average person in the study? Or is that the incredibly, unfortunate person who has literally no other options? They're in a place in life where they don't have access to other health care. They don't know the phone number of the people in Sloan Kettering. They can't fly to the next place. They may not have insurance. This trial is also run globally. It's run in countries where they can't afford anything else, and so they have to stay. So in my opinion, this is not a randomized study. When you have 50% of people in the control arm drop out disproportionately, it's not a randomized study. It's a study of extremely vulnerable people who are willing to put up with an unethical standard of care versus everybody who's eager to get lutetium-177. And randomization itself is violated. The study is not a randomized study. The study should have been halted by an IRB, and the investigator should have been fired for an unethical conduct of a study because they had a study with this kind of dropout. And even with education, it's still off the charts. Now, there's one dot here that mirrors this dot. It's a dot called quizartinib. When the FDA saw the imbalance in dropout, they actually didn't get FDA approval, went to the Oncology Drug Advisory Committee meeting. We never allow this kind of dropout. It really thwarts randomization. So the rationale for the exclusion of certain treatments was they'd never been tested in combination with lutetium PSMA. Well, that's a bad rationale because you don't need to test them in combination. It could be given in lieu of. And then they say patients who had received one taxane were ineligible if they were deemed at baseline to be candidates for receiving a second taxane. What they're saying is, we didn't think they could take cabazitaxel. Okay, they don't think they could take cabazitaxel. They're too frail for that. If that were true, that when the trial ended and they're more frail, they shouldn't get cabazitaxel. But the problem with that is they do get cabazitaxel after the trial ends. 20% of people in the control group get cabazitaxel, meaning that had you given it to them earlier, it would have been even higher. And remember, 40% got it on the way in. So I think all of their explanations are just total nonsense that doesn't add up. They clearly took people who had better options, who could tolerate those better options. Proof they could tolerate it is they tolerated it later, and they gave him a decrepit, unethical standard of care in order to eke out a benefit. Okay, so that's yes?
So the way you explain this sounds so clear, and like how could somebody miss this? And it's published in the New England Journal of Medicine. And so what is happening here? Do we just not have good peer reviewers? Where is that disconnect in our
Well, thank you for that question. I think that's why some people don't like me in cancer, because the way I can explain it is very clearly. Well, I mean, look, okay, so the first thing I'll tell you is I'm not just picking one study. I have a YouTube channel. You can watch the videos of as they come out, there'll be study after study. In my talks, I cycle through the things, but some of these people have heard my other talks. I use Polo trial, grossly unethical. I just gave a talk in Copenhagen where it was about the ethics of trials. And you can just list off many unethical trials. And the classic, here's the ways they're unethical. One, the control arm is not the US standard of care. Two, once you have progression, they run them in countries where there's essentially no care on the back end. So they're not asking the question that the US faces, like, does this have a benefit in our broader landscape of drugs? They're asking the question, does this have a benefit in a world where you don't have access to anything else? And that question also, people say, well, it makes sense for that country, but it doesn't make sense for that country because when the trial ends, they can't afford the other drugs, they can't afford your drug, They're not gonna have access to this anyway. I think it's an exploitative system, takes advantage of injustices in global market. So who's to blame? FDA. Number one to blame, FDA. FDA has allowed this repeatedly. The FDA actually approved lutetium based on this study. They didn't halt it. The reason they say is because, well, it's very active. And I'm the first to concede. I actually think it could win. I don't think it's such a bad drug it couldn't win. I think it could win against a fair control arm, but I haven't seen that study, ever. And actually, they did do a study against cabazitaxel, and it is a tie, isn't it? This is a Michael Hoffman study, Lancet Oncology, if I recall. I think it's only phase 2. But I do think it could win. It has a role. But the Polo, this is another example, olaparib in pancreas, I think is actually horrible. It wouldn't win. It wouldn't win. It was only one. Okay, so one is FDA. Why do they fail? I mean, I think they fail for many reasons. One is the entire structure is captured by the companies, in my opinion. I mean, the number one source of revenue for FDA is, in fact, the amount of money the companies submit. The FDA doesn't view their position as, in fact, and the commissioner previously, Gottlieb, said, our job is not just to the American people. We have to think about our other constituent. Our other constituent is the companies. The people who work, I think, at FDA, their primary place of employment is at the company when they leave. Jeff Bien and I published that in British Medical Journal. And so I think they have every incentive to try to make these things go. I heard one investigator who ran some of these unethical trials say that if we ran the trials the way you wanted, it would just take too long for the results. And I was like, but the results would actually affect the practice we have. That's one. Two, we've done modeling where we show it doesn't take as long as you think. You could target the highest risk people and get the signal very quickly. Now let's talk about IRBs. I think IRBs fail miserably, but that I excuse because the IRB, the people who sit on the IRB, we all know, it's like you were working hard and someday they said, please go sit on the IRB, and you have no bandwidth, they're not paying you anything to do it. And what do you know about prostate cancer? You don't know anything about this. You're getting somebody who is just a total novice. They can't expect you to know everything. And then the fourth thing is the investigators are captured. I mean, in oncology, if you take a field like multiple myeloma, I can think of one person who's an quote-unquote expert in myeloma who has never taken a payment from the companies. They're all taking payments from the companies, So like if you capture 50 people who are experts in the field, there is literally nobody in the field who can tell you that we've got some serious problems here. And then I'd say 5, the professional society's captured. They don't like the message too. The only saving grace is my YouTube video on this has gotten like 5 times as many views as the original presentation in the plenary session of Vision trial. But I think it's a huge problem. And I know, of course, I think that because I wrote a whole book on that called Malignant about these problems, and they're all intertwined. And the net result, I think, is just that you can make a lot of money in this marketplace from a product that may or may not help people. Some of them do help people. That's how we justify the ones that don't. But whether you help people or don't help people, you can make $10 billion, easy. And these are just a few of the ways we manipulate trials, but there are even more. Every year we find a new way to manipulate them. You could start them at the same dose, but have unequal dose reduction schema. That actually happens in the majority of studies that Timothy, a Swiss guy who worked with me, proved. You can run non-inferiority studies with margins so big you can park a school bus in them, like a margin that's beyond the benefit of the drug over placebo. You can play games with censoring. You can play games with control arm. So I think it's one of the biggest problems. Yeah, I'll stop there, but it's my passion project.
So, you talk about how they can basically select out like the patients who are less educated or sicker. Wouldn't they see that when they report their patient demographics?
Yeah, I think some of those things you might see unless they are, no, actually you're not. Here's why. Table 1 demographics come from all the people who started at randomization. They'd have to present the demographics of the people who were disproportionately censored at time point 1, and they don't put that anywhere. But you're right, there would be ways to get at that if you had truly access to the data set. But the way Table 1 is written now, it's based on everyone randomized. It's not based on whether you dropped out. Yeah. Yes?
Not that I'm expecting insurance companies to save us, but
Yeah.
I would think that if I was an insurance company and I was looking at this drug, why would if they would pick this apart and say, you know what, we're actually not going to cover this because we looked into this and, did you already go over this?
No. Keep finishing your question. I'm just trying to find my
For
slide.
our big health system, all of our Kaiser patients, we're not going to cover this chemotherapy because we took the time to further look into it and it's problematic.
Sorry, they have a lot of jokes in there. Okay. Sorry, this is, okay. Here's my answer to, no, I think I pushed this. Okay. Here's my answer to your question about insurance companies. Okay. And one disclosure is I worked with so many companies and so many third parties on what we call cancer pathways. So through many quirks of legislation, insurance providers and pathway providers, they can't say we won't cover an FDA-approved therapy. Often we're mandated. Medicare by law has to pay for every FDA-approved therapy and any therapy recommended by the NCCN category 2A or higher. So like all these players from Kaiser to they're all, but let's talk about United and let's talk about the big insurance companies. They have a different incentive than I think Kaiser and others. But so one is we got to pay for a lot of things. But what we can do is make a pathway. We can basically say that if 80% of your prescribing is this cost-effective way, we'll give you a bonus to your practice at the end of some period of time. So there's all these pathway companies and they're trying to make pathways that basically, deprioritize things that don't work so well, that cost too much, and I've been involved in all these efforts. But here's the crux of the problem with insurance companies. Okay, I think two problems. One is if one insurance company runs a randomized controlled trial of lutetium versus true investigator choice, the moment that trial is resulted, all their competitors will get that information. And so immediately, they don't have a competitive advantage over a competitor. That's one problem. So I think the companies have never expressed an interest in running randomized control trials that could easily cut the budget by a huge amount. But the bigger problem, the Affordable Care Act, Obamacare has a provision that says an insurance company, the profit margin is capped as 20% profit on revenue. So imagine I tell you we're going to go eat pizza tonight for dinner, and you're really hungry, and I tell you, whatever pizza I order, you get to eat 20%, but not 1% more. You can eat 20% of the pizza. Should I order small, medium, or extra large? You're going to say extra large. And actually, at the insurance companies, I think, even though they talk a big game about cost consciousness, they only care about two things. One, they have to buffer year-to-year variability. You cannot have a sofosbuvir one year because the hep C drug will blow the budget. So you didn't plan for that. You didn't have the premium increases that you needed. You have to have year-to-year buffering. So a lot of these tactics are to buffer year-to-year variability. But over a long arc, 15 years, and also to buffer you against your competitors. But over a 15-year time horizon, I think whether insurance companies admit it or not, they make more money if more GDP is in healthcare. We're at 20% GDP in healthcare now. We'll be at 30% before I'm dead, I think. And then like Rome collapsed when 50% of days were holidays, this whole country will collapse when 50% of healthcare spending is in GDP's 50% of GDP's healthcare spending. So I think that they don't have a real strong incentive to cut the cost. I think that's my cynical view. And they certainly don't think 10 years in the future. Now KP I think is different. Kaiser's different. I keep pointing at him because I think he works there. So why Kaiser's different? Because I think Kaiser does have an incentive to be a steward. They do actually have ways they can collect some of that back. But I do think that they're also very interested in keeping the premium low so that they can gain the market share. So I think Kaiser is actually, if I were to say who's the best player in this space, in this city, at like actually giving people drugs that work and not the drugs that are like horrendous, it's not going to be Parnassus. It's going to be Kaiser. It's going to be Kaiser. And if I had to say the worst place, no comment. But I'm surprised actually the VA sometimes, because here I think the doctors have no perverse incentives and the government can save money, but yet I think we give many drugs that I think have no credible evidence. This drug Vyxeos, we have patients on the service who always get Vyxeos induction for AML. It's tested against a control arm that's substandard, 7 + 3 with consolidation plus 5 + 2, which is not what we do. The drug was made by Jazz Pharmaceutical. They took the 2 drugs we were using, and we mixed them at a certain rate, and they mixed it in a 5-to-1 molar ratio and put it in a liposome. And then they took a drug that cost like $4,000 and turned it into a $400,000 drug, and it's basically the same drug. And then they tested it against like a substandard regimen of the old drug, and they got a win. And they've just claimed all this market share because they send drug reps to your office. So if you're like a practicing doctor, who has time to go look through this and draw lines and all this? Nobody's got time. So they just like send the drug rep to your office, and you're like, oh, sounds so good. And then you start prescribing Vyxeos. But I'm surprised that like you see it at VAs. You see a lot of prescribing here that I'm like, oh, you could save $400,000. And I get angry when I'm like the patient. I'm like, what I want for the patient, I want to give the cheaper drug and have somebody go to their house once a day to check on them. That's $50,000. But I can't get that. But I can get a $400,000 medicine that doesn't work. I was like, so that's my second thing. I think in our American healthcare system, we will always pay for things that take lots of money from society and puts it in the hands of a few shareholders. And we will never pay for things that take lots of money from society and distributes it to hundreds of thousands of healthcare workers. Because it's like the lobbying incentive is to consolidate wealth. And healthcare, I cynically view, is often a financial product that's goal is wealth consolidation among the wealthy with the adverse side effect of occasionally improving health for people. But that's not that important. So sometimes I think that's the entire healthcare system in the US. And our GDP has like Switzerland is number 2 at 11%. We're like at 19% as of now. It's like crazy. All right, I won't go on and on. Thank you for coming.
This was so informative.
Oh, thank you.